Hello everyone, welcome to this presentation entitled Revisiting Inductor and Transformer Operation. This presentation is intended to clarify some aspects related to the operation of inductors and transformers that sometimes are misunderstood. So in this video we will see first the operation of the inductor, then we will explain the operation of a transformer. We will see the basic model of a transformer. We will explain what is an ideal transformer. And finally, we will see how to implement an ideal transformer in LTspice. We will be also showing some LTspice simulations to compare the operation of inductors and transformers. Here we have the basic implementation of an inductor and its basic equations. We start with a magnetic core. This core has a length Le, cross-sectional area Ae, a gap G, and a material with a permeability mu. So we put a winding on it with N turns, and then we make a current circulate through the winding. I have shown here a current source, but it can be also a voltage source with a series resistance or a series impedance or whatever. The important point here is that we have this current circulating through the winding, and then we are going to have a voltage across the winding. Here we have the equations that are going to govern this type of device. We have the Faraday's law. The voltage is the number of turns times the derivative of the flux phi with respect to time. So we have a flux inside the core, as we know. And then we have also that the flux is going to be equal to the number of turns times the current divided by the reluctance. The number of turns times the current is also known as the magnetomotive force. So from here we can also obtain this equation. The voltage is going to be the number of turns squared divided by the reluctance times the derivative of the current in time. And this parameter here is what we call the inductance of our inductor. Also, we know how to calculate this inductance from the geometric parameters of our core, and this is the expression that we know very well. And then the inductance, this is the expression for the reluctance. The inductance is equal to the square of the number of turns divided by the reluctance. If you are not familiar with power inductors and how to design a power inductor, I recommend you to take a look at this video, Power Electronics number 4, Quick Design of Power Inductors. Let's take as an example the operation of the inductor with sinusoidal waveforms, and let's calculate the electrical parameters of the inductor. If we know the current which is circulating through the inductor, which is like this, a sinusoidal waveform with an amplitude I, immediately we can calculate the voltage, which is the inductance, as we have seen, times the di dt. And then we can obtain this expression here. So the voltage is going to be cosinusoidal with an amplitude V. That can be obtained with the product of the current times the impedance, which is omega L. We know this very well. We can calculate also the instantaneous power, which is the product of voltage and current. Then we get this expression here. And then using a trigonometrical equivalence, we can say that the power is going to follow this expression here, 1/2. The amplitude of the voltage times the amplitude of the current and times a sinusoidal waveform with twice the angular frequency. And finally, we can calculate the energy that we have in the inductor, the instantaneous energy E. We know that is 1/2 the inductance times the current squared. So we get this expression here. And finally, using again another trigonometric equivalence, we can express this in this way. 1/4 the inductance, the amplitude of the current squared times this expression 1 minus cosine of 2 omega t. So let's take here a look at the different waveforms. We have the voltage in blue, we have the current, which is lagged 90 degrees with respect to the voltage. Then we have in green the instantaneous power. So we can see that follows a sinusoidal waveform with double frequency. And of course, if we calculate the value of the instantaneous power, is going to be equal to 0. We can also represent the instantaneous energy that we have in the inductor, and then we obtain this waveform here, which is a cosinusoidal waveform of double the frequency of the voltage and the current. But in this case, we can see that we have an average value of the energy. So the average value of the energy can be calculated with this expression here, 1/4 times the inductance times the amplitude of the current squared. So this is interesting because even though we don't have average power in the inductor, of course the average power is equal to 0, we have average energy in the inductor when we operate it with a sinusoidal waveform. So the inductor got this average energy somehow during the transient interval before reaching the steady state that we are showing in these waveforms. And this is why we say that inductors store energy in the form of a magnetic field. Let's do an example for this code here, the EFD25. Here we have the different parameters of this code. We have the length, the cross-sectional area. Here we have the AL value in nanohenries, which is 250. And we are going to select this gap of 0.3 millimeters. And then, for example, taking a number of turns equal to 50 with this value of G, then we can calculate the value of the inductance using this expression, and we get that we will have something like 0.625 millihenries. Now we are going to do an LTspice simulation to check the behavior of this inductor. This is the circuit that we are going to use to do the simulation. Here you can see several components. These components correspond to our magnetics library, which has been explained in previous videos. So if you are not familiar with these components, please take a look at this video, Power Electronics number 5. Spice modeling of magnetic devices. Here these components are the winding. Then we have here the reluctance of the core. This is the length, this is the permeability, and this is the cross-sectional area. And here we have the gap. This is the length of the gap, 0.3 millimeters, and this is the cross-sectional area of the gap, which is the same, of course, as in the case of the reluctance. And then we are using here a sensor, current sensor, to measure the current, which is the equivalent to the flux in the core. And then we are supplying our inductor with a sinusoidal waveform of 170 volts amplitude, 100 kilohertz, using a series resistance of 1 ohm to inject the current. We are using here this series capacitor in order to be sure that we are not going to have any DC component through the winding that can appear otherwise in the simulation. And then we are using here this current sensor also to measure the current through the inductor. And then here below we have the calculation of the instantaneous power. We are multiplying the voltage times the current of the inductor, and here we are calculating the energy. So we are multiplying the inductance times 0.5 and then times the current squared, and then with this we get the energy. Here in this component, as is explained in this video, we have this output here, which provides the value of the inductance of the winding. So we are using this output here to calculate the energy here at this input. You can also see all these different components, the multiplier, the gain, the power component, the current sensor, and so on. These components have been presented before in several videos from LTspice 11 to LTspice number 14. This series of videos are entitled How to Create a Simulink Compatible Control Library. So you can download these components from my website. If you are not familiar with this, please take a look also at these videos about this control library. So now let's do the simulation. We are going to run the simulation up to 5 milliseconds and saving data from 4.95 milliseconds. So let's run the simulation. And now we can check the value of the inductance, for example, so we can see the value is 559 microhenries, so it's very similar to the expected value from the calculations. Now we can add the different waveforms. Let's start deleting this one, and then we can show the voltage. We can add another pane and see the current. So we see that the amplitude of the voltage is 170 volts. The amplitude of the current is nearly 500 milliamperes. We can add another pane. And here we can show the instantaneous power. So we can see that this is the instantaneous power. The peak value of the power is 40.7 watts, but the average value is almost zero. As we can see here is 13 milliwatts, so it's very small. And then we can add another pane and show finally the energy. So we can see that now this value here is 0 up to the maximum value, which is 65.5 microjoules, and the average value of the energy is 32.9 microjoules. So we can check that everything is as expected from the theoretical analysis. Now we are going to convert our inductor into a transformer, and for this what we do is to add a secondary on the core. So this secondary is going to have a number of turns, N2, and first we are going to consider that our secondary is with no load, so we have an open circuit at the secondary. So the winding is going to generate a voltage V2 that can be also obtained using the Faraday's law, which is this expression here. And we have also the expression relating the voltage across the primary and the flux in the core. So we have these two expressions, and we have to note that now, because this is the terminal corresponding to this terminal here, and the flux now is entering into the winding, then we know that this terminal here is going to have a positive voltage with respect to this other terminal, and this is the law that we have to use. So from these two equations, we can obtain finally this expression, which is the expression that we know relating the voltages across the secondary and across the primary with the number of turns, with the turn ratio of the transformer. We can also calculate the flux in the transformer using this expression here, the magnetomotive force divided by the reluctance, where the reluctance is this value that we can obtain using this expression here. And finally, what we see is that we have still an inductor. From the primary, we are going to see an inductance with this value, the number of turns in the primary, squared divided by the reluctance. So with this arrangement, we are not taking energy out of this winding. We can only use this winding as a sensor of the voltage across the primary, because as we know, the voltage here is going to be the voltage in the primary times the turn ratio. When things become really interesting is when we connect a load here at the secondary. So now we are going to have a current circulating through the secondary, and this voltage across the secondary and the current across the secondary are in such a way that they are going to generate a flux phi2, which is opposing to the flux of the primary phi1. We can calculate phi1, as we have seen, with the magnetomotive force divided by the reluctance, and we can also calculate phi2 with the same thing, the magnetomotive force divided by the reluctance. Now, the total flux that we are going to have in the core is the difference between phi1 and phi2. So it's phi1 minus phi2. So we have this expression here, the difference between both magnetomotive forces divided by the reluctance. And this expression for the flux, we can work on it, and we can obtain this other expression, the number of turns in the primary, times a current, which is obtained in this way, I1 minus the turn ratio times I2, divided by the reluctance. So we can see that this is a number of turns in the primary times a current divided by the reluctance. This current we can designate it as IM, and we call it the magnetizing current because it's the current that is generating the flux. So we can see that now we have a lower value of the current generating flux. Is the current through the primary minus the current through the secondary transformed into the primary. So we have less current, and therefore we are going to have less flux in the core. And this is the key point of the operation of the transformer. And with this we can obtain the most basic model of a real transformer, which is shown here. We have the magnetizing inductance and we have an ideal transformer. So the magnetizing inductance models the creation of the flux inside the core. We have the magnetizing current circulating through it, and this magnetizing current is equal to the current through the primary minus the current through the secondary times the turn ratio. So knowing the magnetizing inductance, we can calculate the flux using this expression here. The ideal transformer models the relationship between the currents and the voltages with the turn ratio. And here we have other equations. The voltage can be obtained, as we know, using this expression here. The magnetizing inductance can be calculated with this expression. The voltage across the primary, we can obtain also this voltage using the magnetizing inductance times the derivative of the magnetizing current in time. The voltage across the primary, which can be also obtained if we wish using this expression, and of course the relationship between the voltages in the transformer. Note that with this model we are assuming that all the flux in the core goes through both windings, so there is no leakage flux. In this model, as we know, we are not including this effect. In order to include the effect of the leakage flux, we know that we have to include here in series and also in series with the secondary the leakage inductances. But this is not the point of this presentation today. Let's analyze now the behavior of the transformer from the point of view of the voltages and the currents in the transformer. We have here the same figure, here we have the same equations as in the previous slide, but now let's analyze a little bit further the voltages and the currents in the transformer. So we have seen that the voltage is N1, the voltage across the primary is N1 times the derivative of the flux in time. So we have obtained in previous slide this equation, so we can substitute the flux here and obtain this expression, and from this we can designate this value. Here is L11, this other value here is M. So this is the self-inductance of the primary winding, and this is the mutual inductance between primary and secondary. If we do the same with the voltage across the secondary, then we can get this expression. And again, here L22 is the self-inductance of the secondary. They can be obtained with these expressions here. So now we can see that these expressions are similar as the expressions that we have seen in coupled inductors. So we can wonder here what is the value of the coupling factor K. So if we calculate the value of the coupling factor K, which we know that is the mutual inductance divided by the square root of the product of both self-inductances, and substituting these values here, then we can obtain that the coupling factor is equal to 1, which is evident because up to now we have considered that all the flux in the core goes through both windings, so we don't have any leakage flux, so the coupling is perfect. But the point here that sometimes is misunderstood is that the fact that we have a coupling factor equal to 1 does not mean that this is an ideal transformer. We will talk later what is an ideal transformer, but here we have a real transformer with a magnetizing inductance that creates the flux and with a coupling factor equal to 1. So the leakage flux is 0. Now let's talk about the energy stored in the transformer. If we check our model, here we can see that we have an ideal transformer, so there is no way to store energy in an ideal transformer, and we have here our magnetizing inductor. So the only part in which we can store energy is in the magnetizing inductor. So we can calculate this energy using this expression, as we know. So we can see that if we compare the operation of a transformer and an inductor with the same current through the winding, the energy stored in the transformer is going to be much lower because of the effect of the current circulating through the secondary winding. So this is why we say that the transformer does not store energy. It transfers energy from the primary to the secondary and stores very little energy. The higher the value of the magnetizing inductance, the more ideal the transformer is, and the lower energy is stored in the transformer. So let's do now a simulation to check everything. Here we have our model of the transformer. Is the same as in the case of the inductor, but we have added here this secondary with a load, and now here in this part below we are calculating the magnetizing current, implementing this expression that we know. Here we are calculating the value of the inductance, implementing this expression here. Note that in this case we cannot use this terminal to measure the inductance. In these terminals, what is provided is the ratio between the flux and the current through the winding, but in this case is the total current in the winding, which is the current through the primary. So this is not the inductance that we want to calculate, which is the magnetizing inductance. So we use this expression here and these elements to calculate this inductance. And also we are calculating the energy stored in the magnetizing inductance implemented like this. Remember that all these components are from our Simulink compatible control library. Now let's do a quick simulation comparing the operation of the transformer with the operation of the inductor. For this we are going to operate both of them with the same current circulating through the primary winding in the case of the transformer and through the winding of the inductor. So here we have the transformer, we can run the simulation. And here we can measure the value of the current through the primary, and then we can run also the simulation of the inductor and measure the current through the inductor. So in both of them, we can see that the current is nearly 500 milliamperes. We are measuring here at the output of these sensors, here transforming the current into voltage. So it's around 500 milliamperes peak. Now we can compare the magnetic flux density in both cases. If we add here another pane and measure the magnetic flux density, we can see that here is something below 12 millitesla. If we go to the inductor and add another pane and measure the flux density, we can see that here it's much higher, is nearly 100 millitesla. So this is the effect of the current circulating through the secondary, generating a flux inside the magnetic core that opposes the flux created by the primary winding. So finally, we can add another pane and measure the energy that we have in the transformer, and do the same in the case of the inductor. We add another pane and measure the energy. So here we can see that we have an energy of around 33 microjoules average, while here the average energy is lower than 0.4 microjoules, 455 nanojoules. Note that this small change here is not important. It must be an error in the calculation. Probably if we decrease this parameter rel told to 1 milli and run the simulation again, it's going to disappear. Another confusing point when working with transformers is about the air gap of the transformer. Do we really need an air gap in the transformer? For this, we are going to calculate the flux that we have in our transformer. We know that we have this relationship here between the voltage in the primary and the flux. So if we apply a sinusoidal voltage like this to our primary winding, then we can obtain the flux by integrating the voltage. So we solve this integral here, and then we get this expression here. So the flux is going to be cosinusoidal. And also note that when we do this integral, we have to add a constant, which can be any value. In general, we want that this constant is equal to 0, so we are not going to have a DC level of the magnetic flux in the transformer, but we have to take into account that it's possible to have a DC level of the flux inside the core of the transformer, and because the voltages across the primary and across the secondary are the derivatives of the flux with respect to time, there is not going to be any effect, and the AC components of the voltages are going to be related by the turns ratio. So in principle, we can see that a gap is not necessary. The flux, the peak value of the flux, is going to be limited by this expression here, the voltage, the peak voltage applied to the primary divided by the angular frequency times the number of turns of the primary, and the magnetic flux density can be obtained by dividing this expression by the cross-sectional area. So we can see that here the air gap in the transformer takes no effect, and we can limit the peak value of the magnetic flux density using the parameters in this expression. However, sometimes it can happen that we don't have a perfect sinusoidal waveform applied to the primary, and we have a small DC voltage superposed to this AC voltage, like VDC here. So in this case, we are going to have a DC current circulating through the primary, which is limited by the series resistance of the winding Rs. So we have this value of the current, and therefore we can have a DC component of the flux, which is given by this expression here. So in this case, what is going to happen is that the total flux that we have in the core is going to have an AC component, as we have calculated, and a DC component due to this DC component of the input voltage. Therefore, we are biasing the flux, and then we can reach one side or the other of the saturation of the VH curve. So we are not operating exactly around the origin of the VH curve, and then if this DC component is high enough, then we can reach saturation. So in these cases, it's good to have a little gap because we can increase the value of the reluctance. We know that the higher the gap, the higher the value of the reluctance, and therefore we can limit the DC component of the flux also. And same thing can happen if we have a DC component in the current through the secondary, because it can create also a DC level in the magnetic flux. This can happen, for example, when we use a half-wave rectifier at the output of the transformer. And finally, how to make the transformer ideal, and what is really an ideal transformer. In order to make the transformer ideal, what we have to do is to make the reluctance of the core equal to 0. We can do this in various ways. One way is to have a core with a very high value of the cross-sectional area. If AE is very high, tends to infinite, then the reluctance is going to tend to 0. Another possibility is to have an air gap equal to 0 and then use a magnetic material with a very high permeability. But if we increase the value of the length of the core, or we increase the length of the air gap, then we are going into the other direction. We are making our transformer less ideal. So let's see what is happening in our ideal transformer. If the reluctance is almost 0, we are going to have that the flux generated by the primary is going to be almost infinite, because any current circulating through the primary winding is going to create an almost infinite flux. Same thing happens in the secondary, which is the flux created by the current through the secondary opposing the flux created by the primary. But note that the total flux that we are going to have in the core is the difference between them. So the total flux would be infinite minus infinite, which is an indeterminate value. This means that a finite value of the flux can exist in the core, and in fact, in an ideal transformer, a flux must exist in the core because the flux is related to the voltage that we are applying to the primary and to the secondary, and if we are applying a voltage, then using this expression here, we are going to have a flux in the core. Related to the self-inductances and the mutual inductance, we will have that the self-inductances would be equal to infinite, and also the mutual inductance is equal to infinite. But if we calculate the coupling factor of the ideal transformer, we will see that is the same equation that we have seen before, and the coupling factor in this case will be equal to 1. So finally, this is the equivalent circuit of an ideal transformer. Is the same model that we have seen, but now with an infinite value of the magnetizing inductance, which is the self-inductance of the primary winding. So then, as we can see, only the ideal transformer remains in the model. We have these equations relating the voltages with the flux, and then we can obtain these same equations that relate the voltages and the currents in the primary and in the secondary. And in an ideal transformer, we are going to have that the instantaneous powers are going to be equal. The instantaneous power in the primary is going to be equal to the instantaneous power in the secondary. Note that this is not the case when we are considering a magnetizing inductance, because if we have here a magnetizing inductance which is not infinite, then we can say that the average power that is entering into the transformer is equal to the average power that is getting to the secondary, to the load. But the instantaneous powers are not equal because we have the effect of the magnetizing inductance here. Now, how to implement an ideal transformer in LTspice? We can think on using a pair of coupled inductors, as shown here, L1 and L2. Then, using the coupling factor equal to 1, we implement our transformer. And in order to make it ideal, we use a very high value of the magnetizing inductance. Say, for example, here 10 henries. And of course, the inductance seen from the secondary would be the 10 ratio, n squared, times the magnetizing inductance. However, this is not a good solution because if we put here a very high value of the magnetizing inductance, then we are going to include in our system a time constant very high also. So imagine if we have here a series resistance in the primary of 1 ohm, for example, then we will have a time constant of 10 seconds. So this means that we would need to do a long simulation to reach steady state. And this is a problem in some cases. So let's see a better solution to implement an ideal transformer in LTspice. The implementation of an ideal voltage transformer in LTspice is very easy. We only have to use two behavioral sources. We can use a current source here in the primary, which is going to generate a current that follows the expression that we have seen before, which is the current through the secondary. We are measuring this current here with this sensor and multiplying this current by the 10's ratio. And then we use a voltage source here, which is going to generate a voltage, which is the voltage across the primary, which is measured here, and multiplying this voltage by the 10's ratio N2 over N1. And if we want to implement an ideal current transformer, we do the other way. We can use here a voltage source in the primary, which is going to generate a voltage, which is the voltage of the secondary, times the reciprocal value of the 10's ratio, so N1 over N2. And for the secondary, we use a current source, which is going to generate a current, which is the current through the primary, measured here with this sensor, times the reciprocal value of the 10's ratio, N1 over N2. Well, this is all today in this presentation. I hope that it is interesting for you. Please let me know if you have any comment or question. Thank you very much for watching, and I hope to see you in the next video. Goodbye now.